k. So k is a divisor of n. So for instance, if n was 128, k might be 2 or whatever. And then what we're going to do is, well, G was generated by A, so every subgroup of G, which is cyclic, is generated by some power of A, and in fact the nicest power to choose is actually n over k. We could use k, but n over k is slightly nicer for a reason I'll mention in a minute. So let's just make sure this makes sense. I haven't finished the sentence yet. N is the order of G. K is a divisor of n, so n over k is a natural number because k is a divisor of n. We look at that power of A, and then we just look at the subgroup generated by that power of A. So this is a subgroup of G. And the claim is that this function is a bijection. In other words, a one-to-one correspondence. Okay? So there's various things we have to prove here. Well, there are two things we have to prove. We have to prove that this is one-to-one, and we've got to prove that it's onto, in other words, injective and surjective. And the ingredients 1, 2, 3 that I listed before are the ingredients necessary to prove that this is a bijection. But I'm not claiming that I'm proving this here. So to prove that something's a bijection, you've got to prove that it's injective and surjective. And as I said, the ingredients 1, 2, 3 will do that for us. So this looks a bit complicated, but all we're saying is that for each divisor there is a unique cyclic subgroup, and the reason I've chosen n over k here is that the order of phi of k is actually k. So the reason I've chosen n over k rather than k is that then the order of this subgroup coming from k is actually k. So there's a cyclic subgroup of each of each divisor order. Well, that looks a bit complicated, so I think the best thing to do is an example. But this is the fundamental theorem of cyclic groups. Really, as I said, it should be called the fundamental theorem of cyclic subgroups. And the reason why this is a very useful theorem is the thing on the right looks like it's quite complicated, but the thing on the left is just a set of all divisors of n. And just before I do an example, I just want to mention one other thing, which I guess is number 5. Given that we now know what subgroups of G are, I'm just going to mention one other thing which is useful. How do the subgroups fit together? So suppose I've got two divisors, K and L, then we can look at the subgroup generated by A to the K and the subgroup generated by A to the L. Well, the first is a subgroup of the second. Again, it's a number theoretic result that the first is a subgroup of the second if and only if the second power is a divisor of the first one. So this vertical line means divides. So this says L divides K, or if you want to think of it the other way around, K is a multiple of L. And again, that's not too difficult to prove given the ingredients I've already mentioned. So these 5 facts can all be proved, but all I want to do now is an example, and in fact it's along the lines of the one I did in the tutorial yesterday. So let's look at an example. And in fact this is just a kind of version of the example that's in Fraley. We could do any example we like, but let's take G equals, say, Z18. So we're explicitly taking G to be integers modulo 18. So n, the n that I've been talking about is 18. So what's the set of divisors of n? That's the set of divisors of 18. Of course, if n's very big, then working out all the divisors could be a long job. You could get Maple to do it if you wanted. But 18, we can do it by hand, I hope. So those are the divisors of 18. 1, 2, 3, 6, 9, and 18. And what the theorem says is there's a one-to-one correspondence between this set and the set of subgroups. So we can actually list them. So there are 1, 2, 3, 4, 5, 6 subgroups, and they're all cyclic. So armed with that fundamental theorem, we can just write down all the subgroups of Z18. And I'll list them in the way suggested by that function big phi. So the first divisor is 1, but remember the function big phi actually looked at n over k, so I'll follow that pattern. So n is 18 and the first divisor is 1. Perhaps I'm now reverted to Z18, so perhaps I should revert to the additive notation here. Sorry, I'll just cross that out. Z18 I'm thinking about as generated by 1 in the sense that every element of Z18 is 1 plus 1 plus 1 as many times as I need. I'm now using additive notation. So rather than the power, rather than a to the k, that's just been replaced by the multiple k times 1, which actually I would just write as k. So again, it's this flip between multiplicative notation, which I would use in general, and the additive notation for Z18. So the first generator is actually simply 18 over 1, but that really means 18 over 1 times the generator of the original group, which is 1. So that's 18, but modulo 18 is 0. So in fact, this first one is just the trivial subgroup with one element. So the 1 in the denominator here is the order of the group on the other side, as I remarked a few minutes ago. So the first subgroup we write down is the trivial one. And that's generated by 0, or 18 if you want. So remember, 18 is equal to 0 modulo 18. The next divisor is 2. So we've got 18 over 2, which is 9. What's the subgroup generated by 9? That consists of all, well, generally it would be all powers, but remember we're using additive notation, so that's all multiples of 9. So we look at 0, 9, 9 plus 9, 9 plus 9 plus 9, etc. So we get 0, we get 9, but 9 plus 9 is 0. So the subgroup generated by 9 has 2 elements, and that was to be expected because of the 2 here. Okay? And so far, we've only got one generator for the two cyclic subgroups. So this one is generated by 0, and this one is generated by 9 only. The next divisor is 3. So the generator is 6, and we're expecting 3 elements given by adding 6 to itself as many times as we need to. So we get 0, 6, 6 plus 6 is 12, but then if we add another 6 we get back to 0. So as expected, this has 3 elements because of the fact that we were taking the divisor 3. So this is a cyclic subgroup of order 3. So it's actually isomorphic to integers modulo 3. It's generated by 6, but in fact, as you will see quite easily, it's also generated by 12. Because if we do 12 plus 12, we get 6 modulo 18. And then 12 plus 12 plus 12 will give you 0. So let's carry on this pattern. So the next divisor is 6. So we're looking at the generator 3. And we're expecting the subgroup to have 6 elements. So we get 0, 3, 3 plus 3 is 6, 3 plus 3 plus 3 is 9, and so on. So we get up to 15. If we add another 3, we'll get back to 0. So that's 1, 2, 3, 4, 5, 6 elements. So this is a cyclic subgroup of order 6. It's isomorphic to integers modulo 6. And 3 is one of the generators. 15 is another generator. You can see if there are even more generators. But 3 is the generator we've picked because that's actually a divisor of 18. None of the other generators are divisors of 18. So we'll carry on slightly more quickly now. The next generator is going to be 2, which is coming from 18 over 9, because 9 was the next divisor on the list. So this is going to be a subgroup of order 9. So that's isomorphic to integers modulo 9. 2 is a generator, but there will be other generators as well. And finally, our last divisor is 18 itself. So we've got 18 over 18, which is 1. And of course, 1 generates actually the whole group. So can I fit all this on at once? Not quite. So we had 6 divisors, which are listed just fitting on the top, and each divisor gives us a subgroup, a cyclic subgroup, and the way I've listed them started with the smallest, which is the trivial subgroup, and ending with the biggest, which is the whole thing, and in between there are 4 others. And the theorem says that these are the only subgroups of Z18. There are 6 of them. Okay? So we now know all the subgroups of integers modulo 18. And one nice thing to do, as we've done before 2 or 3 times, is to fit these subgroups into a diagram, which is sometimes called the subgroup lattice. So let me try and do that now. So this is the subgroup lattice. So this is just a way of organizing all the subgroups. So we start at the bottom, or you could start at the top if you wanted, with the trivial subgroup, and we draw a line up to the next subgroup, of which the one you've started with is a subgroup, of which it's a subgroup. So, for instance, 0 is a subgroup of both the subgroup generated by 6, which was 0, 6 and 12, and it's also a subgroup of 0 and 9, and there's nothing in between. Okay? And then each of those is a subgroup of 3. Sorry, I haven't got everything on the same page. The one generated by 3 is this, and both the subgroup generated by 6 and the subgroup generated by 9 are subgroups of this. So that's why I've got these lines. The one generated by 6 is a subgroup of 2, and then both of these are subgroups of the whole thing. So the 6 subgroups fit into this lattice diagram. So just to remind you, a line going up the page means that the subgroup at the bottom of the line is a subgroup of the subgroup at the top of the line, and there's nothing in between. Of course, 9 is a subgroup of the top one, but 3 is in between, so that's why there's a line between 9 and 3 here. And notice that this diagram illustrates the fact that one subgroup is a subgroup of another if and only if the order divides. So for instance, the subgroup generated by 9 is a subgroup of the subgroup generated by 3 because 3 divides 9. 2 divides 6, but 2 does not divide 3, so there's no line here. Okay? So in more advanced work, you can look at the subgroup lattice, and that actually can tell you things about the group. But for the moment, we are just regarding this as a nice way to display all the subgroups. And one of the examples in the exercises for the worksheet over the last week was to look at Z36, for instance, and that has an even nicer subgroup lattice. So these are good exercises to do, and all it involves is looking at the divisors of the order. Okay. So I urge you to do some examples yourself. Write down all the subgroups, which results from writing all the divisors of the order down, and then draw the subgroup lattice. And this is a complete description of all the subgroups, in this case of Z18. Okay? So we're going to leave the theory of cyclic subgroups there, but cyclic groups, because they're the groups generated by a single element, they appear in all groups. So we'll be seeing cyclic groups in and among from now on. Okay?